The engineering student raised his hand during Richard's lecture. Professor Feynman, I have a question about electricity. How does it actually flow through wires? Richard put down his chalk. That's a great question, and I can almost guarantee you've been taught the wrong answer. The student looked confused, but I've taken 3 semesters of electrical engineering. I know how electricity works. Tell me what you know. Electricity is electrons flowing through a conductor like water through a pipe. The electrons move from the negative terminal of a battery through the wire and back to the positive terminal. And how fast do these electrons move? Pretty fast. Nearly the speed of light, I think. Richard smiled. There's your first misconception. The electrons move incredibly slowly. About 1 millimeter per second, maybe slower. That can't be right. When I flip a light switch, the light comes on instantly. If electrons only move 1 millimeter, it would take forever. Exactly. So, what's actually happening at Z? The student had no answer. Neither did most of the class. Let me ask you something else, Richard continued. When you turn on a water faucet, how long does it take for water to come out? Instantly. But the water that comes out isn't the water that was in the pipe near the faucet a moment ago. It's water that was further back in the system. So, how does opening the faucet cause water to come out immediately? Because pressure. The whole pipe is already full of water. Opening the faucet releases the pressure, right? The water molecules themselves barely move, but the pressure wave moves quickly through the water. Electricity works similarly, but not quite the same. And that's where everyone gets confused. Richard turned to the board. The problem is that we teach electricity using analogies that are half true. Water in pipes, electrons flowing like a river. These analogies help beginners, but they create false understanding that's hard to fix later. So, what's the truth? The truth is complicated, but I'll try to explain it clearly. First, forget everything you think you know about electricity. Richard drew a simple circuit on the board. Battery, wire, light bulb. When you connect this circuit, what actually happens? Students called out answers. Electrons flow, current moves, energy transfers. All technically correct, but missing the point. Let me tell you what really happens, and it's going to sound strange. He paused for effect. The energy doesn't actually flow through the wire. It flows through the space around the wire. The classroom erupted in objections. That's impossible. Energy needs a medium. You just said electricity flows. Richard held up his hand. I know it sounds crazy, but it's true. The energy that powers your light bulb travels through the electromagnetic field surrounding the wire, not through the wire itself. Then what's the wire for? The wire guides the electromagnetic field. Think of it like a pipe guiding water. But the water is flowing on the outside of the pipe, not inside. The wire creates a pattern that the electromagnetic field follows. A student asked, so, the electrons in the wire don't matter. They matter. They're essential, but they're not carrying the energy. They're more like guides or controllers. They tell the electromagnetic field what pattern to follow. Richard drew another diagram. When electrons move in the wire, even that tiny millimeters, they create electromagnetic fields. Those fields extend out into the space around the wire, and those fields carry the energy. This is the part everyone gets wrong. We teach that electricity flows through wires like water through pipes. But really, wires are just guides for electromagnetic fields that exist in the space around them. So why can't we see these fields? We can measure them. We just can't see them with our eyes. But they're real. They carry real energy. They do real work. Another student spoke up. If energy flows around the wire, why do we need the wire at all? Why not just send electromagnetic fields through the air? Richard smiled. Now you're thinking, and that's exactly what wireless power transmission tries to do. But it's difficult because electromagnetic fields spread out and weaken with distance. The wire keeps them focused and directed. Let's get back to the speed problem. Richard said, you flip a light switch. How long until the light turns on? Almost instantly. Correct. The electromagnetic signal travels at nearly the speed of light, about 300,000 kilometers in a vacuum. In a wire, it's slower, maybe 2-3 of that, but still incredibly fast. But the electrons only move at a millimeter second, right? So, here's what actually happens. When you flip the switch, you close a circuit. This allows electrons throughout the entire wire to start moving all of them simultaneously, or nearly so. Think of it like a train. You have a long line of train cars all connected. When the engine starts moving, all the cars start moving at almost the same time. You don't have to wait for the engine to push each car individually. In the wire, electrons are like the train cars. They're already there, already in the wire, already touching each other. When you complete the circuit, they all start moving together. That signal, the start moving signal, travels at nearly the speed of light. But the actual motion of each electron is very slow. A student raised her hand. So the energy comes from the electromagnetic field. But we need the electrons to move to create that field. Exactly. The electrons create the field by their motion and by their charge. The field carries the energy. The electrons just guide it. This seems overly complicated. Why does it matter? It matters because if you don't understand what's really happening, you can't design better electrical systems. You make mistakes. You waste energy. You create problems. Richard pulled out a power cable. Look at this. Why is it so thick? If electricity flows through the wire, a thinner wire would be fine for low currents. But thick wires are needed because of resistance. Someone said partly, but also because the electromagnetic field extends into the space around the wire. The field needs room. With alternating current, the field pattern is more complex. The wire needs to be shaped and sized to guide that pattern efficiently. Engineers who don't understand this waste money on materials, or create inefficient systems, or make dangerous mistakes. Richard held up a battery. Let's talk about what a battery actually does. Most people think it stores electricity. Does it? Yes. A student ventured, no. It stores chemical energy. When you connect a battery to a circuit, chemical reactions create a voltage difference between the terminals. That voltage difference creates an electromagnetic field. That field extends through space, and that field carries energy to whatever you've connected. The battery doesn't push electrons through the wire. It creates conditions where electrons want to move. The field does the rest. Wait, someone interrupted. If the field carries the energy, why do we need the wire at all? Why not just hold the battery near the light bulb? Good question. Try it. Hold a battery near a light bulb without connecting them with wire. Nothing happens. Why not? Because electromagnetic fields follow specific patterns. They need pathways. The wire provides that pathway. Without the wire, the field disperses randomly and doesn't reach the light bulb with enough intensity to do anything useful. Richard drew more diagrams. This is why circuit design matters. You're not just connecting wires. You're shaping electromagnetic field patterns. Every bend in the wire, every connection point, every component changes how the field behaves. Radio antennas work on this principle. They're designed to send electromagnetic fields out into space without wires, but they're carefully shaped to create the right field patterns. Your house wiring is also shaped to guide fields efficiently. That's why electricians follow specific rules about wire size, spacing, and routing. They're managing fields, not just connecting metal. A student looked frustrated, so everything I learned in basic electricity was wrong. Not wrong, simplified. And those simplifications create misconceptions that are hard to fix. Like what? Like the idea that electricity is a substance that flows. It's not. Current is the movement of charge carriers, usually electrons. But the energy isn't in the electrons. It's in the field. Or the idea that batteries use up their electricity. They don't. They run out of chemicals that can create voltage differences. The electricity was never in the battery to begin with. Or the idea that turning off a light switch stops electricity from flowing. It doesn't stop anything. It breaks the circuit which changes the field pattern, which stops energy from reaching the light. But nothing physical is stopping or flowing. Richard wrote on the board, electricity is not a substance. It's a process. This is the core misconception. People think of electricity as stuff that moves around. But it's really a coordinated dance of electromagnetic fields and moving charges. The fields carry energy. The charges guide the fields. Together, they make electrical devices work. Why do we teach the wrong version, then? Because the right version is complicated. Electromagnetic field theory requires advanced math. Most people don't need that level of understanding. The simplified version works well enough for basic applications. But if you want to really understand electricity, if you want to design novel systems or solve complex problems, you need the truth, not the comfortable simplification. Richard pulled out a puzzle. Let me show you why this matters practically. Imagine you have two wires parallel to each other, separated by 1 meter. One wire carries current. Does the other wire experience any force? Students thought about it. Most shook their heads. Actually, it does. The current in the first wire creates a magnetic field. That field extends through space. The second wire sits in that field. If current flows through the second wire, it experiences a force due to the first wire's magnetic field. This is called the magnetic force between conductors. It's why parallel wires in your walls can vibrate if enough current flows. It's why transformers work. It's why electric motors spin. None of this makes sense. If you think electricity is just electrons flowing through wires, you need to understand fields. Here's a practical example. High voltage power lines. Why do we use high voltage for long distance transmission? Someone answered, less energy loss. Yes, but why? If you think electricity flows through the wire, high voltage doesn't obviously help. But if you understand that energy flows through the electromagnetic field around the wire, it makes sense. Higher voltage means lower current for the same power. Lower current means weaker fields close to the wire. Weaker fields mean less interaction with the wire's resistance. Less energy wasted as heat. More energy reaches the destination. Engineers who don't understand field theory can't optimize these systems. They follow formulas without understanding why the formulas work. Richard returned to the original example, the light switch. Let's think through what actually happens when you flip it. Before flipping, the circuit is open. The battery creates a voltage difference, but there's a gap in the circuit. An electromagnetic field exists between the battery terminals, but it's weak and localized. You flip the switch. The circuit closes. Suddenly, the field can extend through the wire network. The field pattern changes throughout the entire system almost instantly at nearly the speed of light. This field change tells electrons throughout the wire start moving. They all respond together. The coordinated motion creates a stable electromagnetic field pattern that carries energy from the battery to the light bulb. The electrons themselves barely move, but the field moves quickly. The energy flows through space, guided by the wire, and reaches the light bulb almost instantly. The light bulb filament resists electron flow. This resistance causes the electrons to lose energy, which heats the filament, which creates light. But the energy the electrons lose came from the field, not from the electrons themselves. See the difference? In the simplified model, electrons carry energy through the wire. In reality, fields carry energy through space, and electrons just help guide those fields. Now, I'll tell you something even stranger. Richard said, everything I've just described is still a simplification. Groans from the students. In quantum mechanics, we learned that electromagnetic fields aren't smooth. They're made of particles called photons. And electrons aren't really particles either. They are quantum objects that behave like both particles and waves. So what we call current is really the quantum mechanical behavior of electron wave functions in a conductor. And what we call electromagnetic fields is really the quantum behavior of photons. But we don't need quantum mechanics to design circuits and electrical systems. The classical field theory I've described works perfectly well for almost all practical applications. This is a pattern in physics. We teach simplified models first, then more accurate models later. Each model is useful for different purposes. The trick is knowing which model to use when. For household electricity, thinking about electrons flowing through wires is fine. For radio design, you need field theory. For quantum computers, you need quantum mechanics. The mistake isn't using simplified models. The mistake is thinking the simplified model is the complete truth. A student asked, so will we ever understand the complete truth about electricity? Maybe, maybe not. Every time we think we understand something completely, we discover deeper layers. 100 years ago, we didn't know about quantum mechanics. Who knows what we'll discover in another 100 years? But that's okay. Science isn't about reaching final truth. It's about building better and better models. Models that predict more, explain more, and enable more. Richard looked at the original student who'd asked the question, so, how does electricity flow through wires? The student thought carefully. Electricity doesn't really flow. Electromagnetic fields carry energy through space. Wires guide those fields. Electrons move slowly in response to the fields. Together, this system transfers energy from one place to another. Better. Not perfect, but better. You're thinking in terms of fields now, not just particles. Here's what I want you to remember. Reality is always more complex than our models suggest. When someone asks how electricity works, there's no single correct answer. There's the answer appropriate for their level of understanding. For a child, electricity flows through wires like water through pipes. For an engineering student, current is the movement of charge carriers through conductors. For a physicist, energy flows through electromagnetic fields in the space surrounding conductors. For a quantum physicist, it's all wave functions and probability amplitudes. All of these answers are true at their respective levels. None is complete. Choose the model that helps you solve the problem you're facing. The lecture continued, but something had changed. They were no longer thinking about electricity as a simple substance flowing through wires. They were beginning to see the deeper reality, the invisible fields, the complex dance of energy and charge. It would take years to fully understand. Richard knew that, but the seed had been planted. The comfortable misconception had been challenged, and that was the first step toward real understanding. Not the final truth, but a better approximation, a more useful model, a deeper insight. That's all science could offer, and sometimes that was.